Most aircraft that flew combat missions over North Vietnam between 1965 and 1973 returned to their bases. Few returned without damage. The Republic F-105 Thunderchief carried the heaviest burden of the air war during the Rolling Thunder campaign, flying more strike missions into defended airspace than any other American aircraft. This was not a role it had been designed for, but one thrust upon it by strategic necessity and the absence of viable alternatives. The F-105 was built in the 1950s as a supersonic nuclear strike aircraft, intended to penetrate Soviet airspace at low altitude, deliver a single tactical nuclear weapon, and escape at maximum speed. It was engineered for a mission that would last minutes, not for the sustained conventional bombing campaign that would define the Vietnam War. By 1965, it had become the primary instrument of American tactical air power over North Vietnam, and the consequences of this operational mismatch became evident almost immediately. The F-105 was a large aircraft by fighter-bomber standards. It weighed over 50,000 pounds fully loaded, could carry up to 12,000 pounds of conventional ordnance, and was powered by a Pratt & Whitney J75 turbojet engine that produced 26,500 pounds of thrust with afterburner. It was fast, capable of exceeding Mach 2 at altitude, and it had the range to reach targets deep inside North Vietnam from bases in Thailand without requiring multiple aerial refuelings. These capabilities made it indispensable, but they also made it a target. The F-105's size, its predictable flight profiles, and the concentration of its operations into a relatively small number of heavily defended target areas exposed it to a level of defensive fire that few aircraft in history have endured with such consistency. The typical mission profile began before dawn. Pilots attended briefings where target coordinates, defense locations, weather conditions, and egress routes were discussed in detail. Intelligence officers, intelligence, presented the latest information on surface-to-air missile sites known as SAM sites and anti-aircraft artillery positions. The information was often incomplete. Defenses moved, new sites appeared overnight. The briefings provided a framework, not certainty. After the briefing, pilots walked to their aircraft in the pre-dawn darkness, conducted pre-flight inspections, and climbed into cockpits that still carried the smell of hydraulic fluid, jet fuel, and the faint metallic odor of previous battles. Engine start was a carefully orchestrated sequence. The J-75 required precise fuel flow and ignition timing. A hung start, where the engine failed to reach self-sustaining speed, could scrub a mission or force a last-minute aircraft swap. Ground crews stood by with fire extinguishers, watching exhaust temperatures, listening for abnormal sounds. Once the engine stabilized, the pilot checked flight controls, hydraulic pressures, electrical systems, and weapon stations. Each check was a ritual, repeated hundreds of times but never performed mechanically. A missed warning light, an abnormal gauge reading, could mean the difference between completing a mission and aborting over hostile territory. Takeoff from bases in Thailand, particularly Takhli and Korat, involved long taxi queues as strike packages assembled. A typical package included 16 to 20 F-105s, accompanied by F-4 Phantoms flying escort and Wild Weasel aircraft configured to suppress enemy air defenses. The formations were large, complex, and vulnerable to disruption. Aircraft spacing had to be maintained. Radio discipline was critical. Any deviation from the plan created cascading problems. The takeoff roll was heavy, the aircraft laden with fuel and bombs, accelerating slowly until reaching rotation speed. The gear retracted with a thud felt through the airframe, and the formation began a slow climb toward the tanker rendezvous point over Laos. Aerial refueling was a necessary but dangerous phase of the mission. The F-105's internal fuel capacity was insufficient for deep strikes into North Vietnam with a full bomb load. Tankers, usually KC-135 Stratotankers, orbited at predetermined coordinates, trailing refueling drogues or extending boom nozzles. The rendezvous had to be precise. Delays burned fuel. Weather could scatter the formation. The refueling itself required steady hands and concentration. The F-105's refueling receptacle was located behind the cockpit, and connecting to the tanker's boom required maintaining a precise position relative to a much larger aircraft while flying at 300 knots. Turbulence made the task harder. So did the knowledge that every minute spent refueling was a minute closer to the target. After refueling, the formation turned northeast, crossing into North Vietnamese airspace. The transition was marked not by a visible boundary but by a change in radio traffic and an increase in tension. Radar warning receivers began to display threat signals. North Vietnamese early warning radars tracked the incoming formation, and air defense commanders coordinated responses. The defenses were layered, sophisticated, and deadly. Surface-to-air missiles provided long-range coverage around key targets. Anti-aircraft artillery created overlapping zones of fire at medium and low altitudes. MiG interceptors, vectored by ground controllers, waited to exploit vulnerabilities in the strike formation. The defenses were not static. They adapted, learned, and became more effective over time. The descent to low altitude, conducted to evade radar detection, subjected the aircraft to intense physical stress. The F-105 was designed for high-speed flight, but at low altitude, turbulence and dense air created buffeting that shook the entire airframe. Pilots flew in loose formation, maintaining visual contact while maneuvering to avoid terrain and obstacles. The landscape of North Vietnam, particularly in the Red River Delta, was a patchwork of rice paddies, rivers, and low hills. Navigation required constant attention. A wrong turn could take the formation into unplanned defenses or cause a fuel crisis on the return leg. The low-altitude run consumed fuel rapidly, and there was little margin for error. Approaching the target area, the formation climbed to attack altitude, trading the relative safety of low-level flight for the visibility and bombing accuracy needed to hit the target. This climb, the pop-up maneuver, was the most dangerous phase of the mission. It exposed the aircraft to the full weight of the defenses. Anti-aircraft artillery opened fire immediately. The sky filled with black puffs of smoke, each representing an exploding shell. The shells were time-fused to detonate at specific altitudes, creating a barrage that did not need to score direct hits to be effective. Proximity was enough. Fragments from airburst shells traveled at high velocity in all directions. They perforated wings, punctured fuel cells, severed hydraulic lines, and damaged control surfaces. Pilots described the sound of flak impacts as a sharp metallic rattle, distinct and unmistakable. The aircraft shuddered with each hit, and warning lights illuminated on the instrument panel. Hydraulic pressure warnings, fire warnings, fuel quantity warnings. The warnings had to be prioritized, processed, and acted upon while maintaining formation, acquiring the target, and preparing for weapons release. The mental workload was extreme. There was no time for hesitation. Decisions had to be made in seconds, often with incomplete information and under fire. Surface-to-air missiles added another dimension to the threat. The SA-2 Guideline, a Soviet-designed radar-guided missile, was the primary SAM system deployed around North Vietnamese targets. The missile was large, fast, and carried a powerful warhead. Launch detection was provided by radar warning receivers, which alerted pilots to the characteristic signals of the missile's guidance radar. The alert, a distinctive tone in the headset, triggered immediate defensive action. Pilots broke formation, rolled inverted, and pulled hard toward the missile, attempting to defeat the guidance system through high-G maneuvering. The maneuver was violent, stressing both the aircraft and the pilot. G-forces compressed the pilot into the seat, grayed out vision, and made control inputs difficult. The missile's trajectory had to be tracked visually while executing the brake, a task that required focus and experience. Not all missiles were defeated. Near misses detonated close enough to cause catastrophic damage. The blast wave buckled skin panels, shattered canopies, and disabled flight controls. Fragmentation perforated the fuselage in hundreds of places, creating a sieve-like pattern that maintenance crews would discover later. Aircraft that survived near misses often returned with asymmetric damage, one side of the airframe shredded while the other remained relatively intact. The randomness of the damage reflected the chaotic nature of the engagements. Weapons release was the culmination of the mission, but it was not a moment of relief. The bombs, typically 750-pound general-purpose bombs carried on multiple stations, had to be released in a precise sequence to maintain aircraft balance and stability. The release was felt as a sudden lightening of the aircraft, a distinct change in handling characteristics. The pilot then rolled into a hard diving turn, the egress maneuver, designed to minimize exposure to defenses while exiting the target area. The egress was flown at maximum speed, often with afterburner engaged, descending back to low altitude where terrain and distance would provide some protection from SAMs. The return flight was not safe. Fuel management became critical. Combat maneuvering and afterburner use consumed fuel faster than planned. Pilots calculated range to the tanker, assessed fuel reserves, and decided whether to divert to alternate bases or attempt the rendezvous. Aircraft with battle damage faced additional challenges. Fuel leaks common from punctured tanks reduced the available fuel. Damaged engines, running hot or producing less thrust, increased fuel consumption. Some aircraft did not make it to the tanker. They diverted to emergency airfields in Laos or Thailand, landed with minimal fuel, or were abandoned when fuel exhaustion was imminent. Those that reached the tanker faced another refueling, this time with damaged aircraft and exhausted pilots. The refueling was often more difficult than the first. Damaged flight controls made precise positioning harder. Hydraulic leaks reduced control authority. Pilots fought to keep the aircraft stable while the boom operator guided the refueling nozzle into the receptacle. The process could take multiple attempts. Each failed attempt consumed more fuel and increased the risk of not making it home. Landing back at base revealed the full extent of the damage. Ground crews met the aircraft on the taxiway, inspecting for fuel leaks, hydraulic fluid trails, and visible structural damage. Pilots taxied slowly, aware that damaged landing gear or brakes could fail at any moment. Once parked, the aircraft was surrounded by maintenance personnel who began immediate damage assessment. Panels were opened, systems were inspected, fluids were checked. The damage reports, recorded on standard forms, documented every hole, every leak, every malfunction. The reports from a single mission could run multiple pages. The most common damage involved anti-aircraft artillery fragments. Small perforations, ranging from a few millimeters to several centimeters in diameter, peppered the wings and fuselage. Each hole required inspection to determine whether underlying structure had been compromised. If the damage was limited to skin, a simple patch could be applied, a piece of aluminum sheet riveted or bonded over the hole. If structural members were damaged, the repair became more complex. Ribs, spars, and stringers had to be reinforced or replaced. The work required removing large sections of skin to access the internal structure, a process that could take days. Hydraulic systems were particularly vulnerable to fragment damage. The F-105 had two independent hydraulic systems, designated PC-1 and PC-2, operating at 3,000 pounds per square inch. The systems powered flight controls, landing gear, brakes, speed brakes, and the weapons release mechanisms. Hydraulic lines ran throughout the aircraft, often in areas exposed to enemy fire. A single fragment could sever a line, causing immediate fluid loss and system depressurization. The loss of one system was manageable. The loss of both was critical. Pilots practiced emergency procedures for dual hydraulic failure, but the procedures relied on manual reversion systems that were difficult to operate and provided limited control authority. Repairing hydraulic damage required draining the system, locating the severed line, cutting out the damaged section, and installing a new line segment with proper fittings and torque specifications. The hydraulic fluid itself, MILH 5606, was toxic and flammable, requiring careful handling. Refilling the system after repair required bleeding air from the lines, a tedious process that had to be done correctly to ensure proper system function. Incomplete bleeding could cause erratic control behavior or system failure in flight. Fuel system damage was equally common and potentially more dangerous. The F-105 carried fuel in multiple internal cells and external tanks. The internal cells were integral to the wing and fuselage structure, meaning they were part of the airframe itself rather than separate bladders. This design saved weight but made repairs more difficult. A puncture in an integral fuel cell required access from inside the wing or fuselage, often necessitating the removal of access panels, inspection doors, and sometimes entire skin sections. The interior of the fuel cell had to be cleaned, the puncture located, and sealant applied. The sealant, a rubberized compound, had to cure for several hours before the cell could be pressure tested. Fuel leaks that were not immediately apparent during post-flight inspection often became evident during the next flight. Pilots reported fuel quantity drops inconsistent with consumption rates or fuel stains appearing on the aircraft during flight. Fuel leaking from the aircraft in flight created a fire hazard, particularly near hot engine components or in the presence of electrical arcing. Some leaks were tolerable, minor seepage that did not significantly affect fuel reserves or create immediate danger. Others required grounding the aircraft until repairs were completed. Engine damage from ingestion of debris or battle damage to the engine bay was less frequent but more serious. The Pratt & Whitney J75 was a robust engine, but it operated at extreme temperatures and pressures. Ingestion of even small objects could damage compressor blades, reducing efficiency and thrust. Larger objects could cause catastrophic failure. Pilots monitored engine parameters constantly, watching for signs of abnormal operation. Elevated exhaust gas temperature, reduced RPM, abnormal vibration, or unusual noise indicated potential engine problems. Some issues could be managed in flight by reducing power settings. Others required immediate shutdown and single-engine flight back to base. Engine bay fires caused by fuel or hydraulic fluid leaking onto hot engine surfaces were among the most feared emergencies. The fire warning system, consisting of thermal sensors in the engine bay, alerted the pilot to the presence of fire. The immediate response was to shut down the affected engine and discharge the fire suppression system, which flooded the engine bay with fire-extinguishing agent. If the fire did not extinguish, the aircraft had to be abandoned. Pilots ejected from F-105s over North Vietnam, over Laos, and over Thailand due to engine fires that could not be controlled. Some were rescued, others were not. Avionics damage, while less immediately life-threatening than structural or propulsion damage, significantly degraded mission effectiveness. The F-105 carried a complex suite of electronic systems, including a bombing computer, radar warning receiver, inertial navigation system, and communication radios. These systems were housed in avionics bays located in the nose and aft fuselage, areas exposed to enemy fire. Fragment damage to avionics bays could disable multiple systems simultaneously. Electronic components, built with vacuum tubes and early transistors, were sensitive to shock and vibration. A hard landing, a nearby missile detonation, or even the vibration from sustained low-altitude flight could cause intermittent failures that were difficult to diagnose. Troubleshooting avionics problems required specialized test equipment and trained technicians. The process was systematic but time-consuming. Technicians followed fault isolation procedures, testing circuits, swapping modules, and checking connections. Some problems were obvious, such as severed wiring or shattered components. Others were subtle, intermittent faults that appeared under specific conditions and disappeared during ground testing. These intermittent failures were frustrating for maintainers and dangerous for pilots who depended on the systems to navigate, deliver weapons, and avoid threats. The radar warning receiver, which alerted pilots to enemy radar signals, was a critical defensive system. It provided early warning of SAM launches and fighter intercepts. When the system failed, pilots flew without this warning, relying instead on visual lookout and radio calls from other aircraft. The loss of situational awareness increased vulnerability and forced pilots to fly more conservatively, which in turn reduced mission effectiveness. Repairing or replacing a failed radar warning receiver required access to the equipment bay, removal of the faulty unit, installation of a replacement, and system calibration. The work could take hours, and replacement units were often in short supply. Communication radios, both UHF and VHF, were essential for coordination within the strike package and for emergency communications. Radio failures were common, caused by battle damage, electrical faults, or environmental degradation. A pilot without radio communication could not receive updates on threats, could not coordinate with other aircraft, and could not call for rescue if shot down. Maintenance crews prioritized radio repairs, but the work required specialized knowledge and access to limited spare parts. Some aircraft flew missions with degraded radio capability, relying on hand signals and pre-briefed procedures to maintain coordination. The 20mm M61 Vulcan cannon, carried internally in the F-105, was intended for air-to-air combat but was occasionally used for strafing ground targets. The cannon was a 6-barrel rotary weapon capable of firing 6,000 rounds per minute. It was mechanically complex and prone to malfunctions, particularly when exposed to the dust, humidity, and vibration of combat operations. Ammunition feed jams, caused by misaligned feed chutes or damaged rounds, were common. The gun's hydraulic drive motor, which rotated the barrels, could fail due to hydraulic system damage or electrical faults. Clearing a jammed gun required manually rotating the barrels, removing the jammed rounds, and inspecting the feed mechanism for damage. The cannon's firing vibration was intense, felt throughout the aircraft. Extended bursts could cause structural fatigue in the gun bay and surrounding airframe. Some aircraft developed cracks in the gun bay structure requiring reinforcement. The spent shell casings and links ejected through a port in the fuselage occasionally caused damage to the aircraft's skin or became lodged in control surface hinges. Maintenance crews had to inspect the ejection path and surrounding areas after each mission where the gun was fired. Structural fatigue, distinct from battle damage, emerged as a significant problem as the war progressed. The F-105 was designed for a service life of 4,000 flight hours under normal peacetime operations. Combat operations, with their high-G maneuvering, low-altitude buffeting, and heavy landing loads, accelerated fatigue accumulation. Cracks appeared in areas not initially identified as critical, including wing attachment points, landing gear support structures, and fuselage longerons. These cracks, if undetected, could propagate to critical lengths and cause structural failure. Non-destructive inspection methods, including X-ray, ultrasonic, and dye-penetrant testing, were used to detect cracks before they became dangerous. Inspection intervals were shortened as patterns of cracking became evident. High-time aircraft underwent more frequent and thorough inspections. Some cracks were discovered during routine maintenance. Others were found only after an incident, such as abnormal handling characteristics or unusual noises reported by pilots. The discovery of a crack triggered a detailed inspection to determine its extent and the appropriate repair method. Repairing structural cracks required precision and skill. Small cracks could be stop drilled, a technique where a hole was drilled at each end of the crack to prevent further propagation. Larger cracks required the installation of reinforcing plates or doublers, metal sections riveted or bonded over the cracked area to restore strength. In some cases, entire structural components had to be replaced, a process that required disassembly of surrounding structures, careful removal of the damaged part, and installation of a new or refurbished component with precise alignment and torque specifications. The landing gear, subjected to repeated high-load landings, was a particular area of concern. The F-105's main landing gear consisted of single wheels on each side, retracting into the fuselage. The gear struts absorbed landing loads through hydraulic shock absorbers. Hard landings, common when returning with battle damage or low fuel, compressed the struts beyond normal limits, sometimes causing damage to the strut structure, attachment fittings, or the retraction mechanism. The gear had to be inspected after every hard landing, a process that included measuring strut compression, checking for hydraulic leaks, and inspecting attachment points for cracks or elongated bolt holes. Tire wear was accelerated by high-speed landings and heavy braking. Brake temperatures during landing could exceed safe limits, causing brake fade or fire. Maintenance crews monitored brake temperatures with infrared thermometers and allowed sufficient cooling time before servicing the brakes. Brake inspections revealed worn pads, scored rotors, and damaged hydraulic pistons. Brake overhaul was a routine maintenance task performed frequently on aircraft flying regular combat missions. Environmental conditions in Southeast Asia created challenges beyond combat damage. The heat and humidity caused rapid deterioration of rubber seals, electrical insulation, and protective coatings. Monsoon rains flooded aircraft parking areas, exposing avionics bays and engine compartments to water intrusion. Moisture in electrical systems caused corrosion and short circuits. Avionics modules had to be removed, dried, and tested before reinstallation. Corrosion, particularly in aluminum structures, appeared in joints, seams, and fastener holes. Corrosion treatment required removing the affected material, applying corrosion inhibitors, and sealing the area to prevent recurrence. The open-air maintenance environment, with aircraft parked on concrete ramps exposed to sun and rain, made corrosion prevention difficult. Protective covers were used when available, but resources were limited. Maintenance crews worked in the open, often in temperatures exceeding 100 degrees Fahrenheit, with high humidity that made physical work exhausting. Night shifts worked under portable floodlights, which attracted insects and created harsh shadows that made detailed inspection difficult. Spare parts availability was a persistent problem throughout the war. The supply system, designed for peacetime operations, could not keep pace with combat attrition rates. Critical components, including engines, avionics modules, hydraulic actuators, and structural assemblies, were chronically in short supply. Maintenance crews resorted to cannibalizing damaged aircraft, removing serviceable parts to keep mission-capable aircraft flying. This practice created a pool of partially stripped airframes that became progressively harder to return to service. Some cannibalized aircraft were eventually written off, their usable parts distributed across the remaining fleet. The logistics chain from depot facilities in the United States to forward bases in Thailand involved multiple transportation modes and handling points. Parts could be lost, misdirected, or delayed. Urgent requests for critical parts were expedited through special channels, but even expedited shipments took days or weeks. Maintenance crews learned to improvise, fabricating parts when possible, modifying existing parts to fit different applications, and keeping detailed records of what worked and what did not. Engine availability was particularly critical. The J-75 engine required overhaul at intervals determined by operating hours and cycle counts. Combat operations accelerated wear, reducing the time between overhauls. Engines were shipped to depot facilities for overhaul, but the turnaround time was measured in months. The result was a shortage of serviceable engines, limiting the number of aircraft that could be maintained in mission-capable status. Some aircraft sat idle, waiting for engines, while others flew missions with engines that had exceeded recommended overhaul intervals. The maintenance burden grew as the war continued. The fleet aged. Cumulative damage increased. The number of aircraft requiring major repair grew faster than the capacity to complete the repairs. Maintenance man-hours per flight hour, a standard measure of maintenance intensity, increased steadily. What had been a sustainable maintenance workload in peacetime became an unsustainable burden in combat. Maintenance crews worked longer hours, took fewer breaks, and deferred personal needs to keep the aircraft flying. The pressure to maintain high sortie rates created tension between operational demands and maintenance realities. Wing commanders, under pressure to meet target requirements, pushed for maximum aircraft availability. Maintenance officers, responsible for aircraft safety and long-term fleet health, resisted shortcuts that compromised safety. The balance was difficult to maintain. Some maintenance tasks were deferred not because they were unimportant, but because there was insufficient time and resources to complete them before the next mission. The deferred maintenance accumulated, creating a backlog that grew larger over time. Quality control in this high-pressure environment was a constant challenge. Inspectors reviewed completed maintenance work, checking for proper torque on fasteners, correct installation of parts, and compliance with technical procedures. Errors were found and corrected, but the inspection process added time to an already compressed maintenance schedule. Some errors were not discovered until the aircraft flew again, resulting in in-flight malfunctions that required emergency procedures and sometimes led to aborts or diversions. The psychological toll on maintenance crews is difficult to quantify, but impossible to ignore. These were young men, many barely out of technical school, working under conditions of stress, heat, and exhaustion. They knew that their work directly affected the safety of the pilots who flew the aircraft. A missed crack, an improperly installed part, an overlooked discrepancy could result in an aircraft loss and a pilot's death. The responsibility was crushing. Some coped by focusing narrowly on their specific tasks, following procedures mechanically, avoiding thoughts of the larger consequences. Others internalized the stress, developing sleep problems, anxiety, and physical symptoms of exhaustion. The bond between pilots and maintenance crews was built on mutual dependence. Pilots trusted that the aircraft had been properly maintained, that the repairs were sound, and that the systems would function as designed. Maintenance crews took pride in their work, knowing that they were directly supporting combat operations. When an aircraft was lost, maintenance crews reviewed the records, searching for any indication that a maintenance issue had contributed to the loss. The reviews were thorough and sometimes painful, but they were necessary to identify problems and prevent future failures. The F-105 force reached its peak effectiveness in 1966 and 1967, when sortie rates were highest and target lists longest. During this period, the maintenance burden was most intense. Aircraft flew multiple missions per day. Turnaround times between missions were measured in hours. Battle damage repairs were prioritized, with less critical maintenance deferred to later opportunities that rarely materialized. The result was a fleet that was operationally effective, but mechanically degraded, held together by the skill and determination of the maintenance crews and the resilience of the basic airframe design. By 1968, attrition and fatigue had taken their toll. Nearly half of the F-105s built had been lost to all causes. The remaining aircraft showed extensive evidence of repair and modification. Some had been rebuilt multiple times. Inspection records documented hundreds of repairs on individual airframes. The aircraft were no longer new. They were veterans, bearing the scars of sustained combat in a way that few aircraft before or since have experienced. The end of Rolling Thunder brought a reduction in operational tempo, but not an end to the maintenance challenges. Aircraft that had survived the most intense period of operations required depot-level overhaul. Complete teardown inspections revealed the full extent of structural fatigue, corrosion, and system degradation. Many aircraft required replacement of major structural components, complete rewiring of electrical systems, and overhaul of all major subsystems. The cost of these overhauls, in both time and money, was substantial. Some aircraft were determined to be beyond economical repair. Their airframes had accumulated too much damage, too many flight hours, too many stress cycles. These aircraft were retired, their components harvested to support the remaining fleet. Others were transferred to Air National Guard units, where they continued to serve in less demanding roles. The operational career of the F-105 as a frontline strike aircraft ended not with a single event, but with a gradual withdrawal as newer aircraft replaced them and as the remaining airframes reached the end of their useful lives. The legacy of the F-105 in Vietnam is inseparable from the maintenance effort that sustained it. The aircraft performed missions it was never designed for, under conditions more severe than its designers anticipated, for longer than anyone expected. It did so because of the men who kept it flying, who repaired the damage, who improvised solutions, and who worked through exhaustion to ensure that missions could continue. The aircraft rarely returned unchanged because the missions it flew and the defenses it faced ensured that every flight extracted a price. The fact that it returned at all is a testament to both the resilience of the design and the dedication of those who maintained it. Please subscribe if you want to hear more military stories.